So we said, cool, you want to come up with, if you have a uniformly continuous function, you would like to come up with an extension of that function to a continuous function on a slightly larger domain. Let's use exactly that formula to define our continuous function. Oh, it wasn't necessarily uniformly continuous. We assume that that limit exists at our limit point. So there's a definition of a function. We proved that it was a function. It obviously extends the function f. And we proved last time that this function is still continuous, at least on the set U, where we assumed f was continuous, which isn't nothing. And there was this like fancy, oh, well, play the epsilon divided by 3, delta divided by 3, or divided by 2. We had to divide by 2? Okay, I'll play that game. The proof for continuity at the limit points will be pretty similar. I don't know if people would like to start today just finishing off the proof. Let's do it. So, right, so maybe this will seem very fast, but there's the definition of the function we're going to use. Maybe it's worth writing that down. Right there, that's in terms of p. So let's prove that this function is continuous when p is a limit point of u. So let's suppose p is a limit point of u. Let's try to prove continuity at that limit point. If p is a limit point of u, then what is g of p by definition?
As x goes to p, then x.
Yeah, it's back. Right, that's how you read case-wise, piecewise functions. And let's unravel that in terms of the definition of the limit. So by the definition of the limit, then there must exist some positive quantity delta. Oh, well, no, earlier on, like way distantly back, we considered any epsilon bigger than 0. So we considered any epsilon bigger than 0. So we have a limiting statement there. So the definition of the limit then gives us that there exists some positive quantity. I'll call it delta 1 because that probably won't be the delta that I need at the end of the day. Such that if 0 is less than y minus p is less than delta, then the absolute value of g of p minus f of y must be less than epsilon, but we all well know that we could put any positive quantity there. Maybe you are guessing already that epsilon over 2 is the right choice. Maybe you're not. I'll not guess yet. But that can be any positive number I want. Oh, but I'm supposed to like color code these. That might not, epsilon might not be the right choice. So now, let's consider any x in the closure of U. If I want to prove continuity, then I should assume that the absolute value of x minus p is less than some positive amount. And right now, the only positive amount we have is delta 1. Now, this quantity x is in the closure of U. So it has two choices. Either it is itself in U, or it is a limit point of U. Let's see what happens in each case. Suppose that x is itself in U. Now, by assumption right now, we said the absolute value of x minus p is less than delta 1. Well, wait, so then this x value is an x value which is within a distance of delta 1 of p let's add an interjection. Assuming that x is not itself equal to p, then we have 0 is less than absolute value of x minus p is less than delta 1. So we have the hypothesis of this if then being true. So what can we conclude? The conclusion of the if then? So the absolute value of g of p minus f of x is less than epsilon. Oh, but wait, x is a point in u, so g of x and f of x are the same thing. Making that substitution, we get g of x minus g of p is the same thing as absolute value of f of x minus g of p. And hey, we've already seen that that's less than epsilon, so we're done. I guess there's like an error here. What happens if x is actually equal to p?
We don't have that.
Why not?
Because then the assumption doesn't hold. Because we wouldn't have 0 is less than absolute value of x minus p is less than delta.
Yeah, so we wouldn't be able to use the same argument. We'll need to use a different argument. So if x is secretly equal to p, I'll put that right here. On the other hand, right, because whenever you assume something, if it's not an assumption you're allowed to make, then you need to see what happens when that assumption is false. On the other hand, when x is equal to p, well, if x is equal to p, then what can you tell me about g of x minus g of p? Zero. Which is less than epsilon, again, as required. So it's still okay when x is equal to p, but it is a case we have to deal with. How does everyone feel about that? Happy so far? Okay, so let's move on to case 2b. Let's suppose that x is, instead of being a point in u, is a limit point of u. So tell me, what is g of x equal to? Well, it's the limit as some input approaches x of f of that input. So I'll just pick a variable named y. So g of x is equal to the limit as y approaches x of f of y. Everyone with me so far? So, the same game again. There exists a positive quantity. It won't be delta 1, it's a different point, delta 2, such that if the absolute value of x minus y is less than delta 2, then absolute value of g of x minus g of y is less than epsilon. Everyone feel pretty okay so far? Now, another thing we know, since this point x is a limit point of u, there exists some y such that y isn't equal to x, and the absolute value of x minus y is less than any positive number you can come up with. And I don't know, we probably want like to use f of y to approximate g of x, one would think. So I'd probably need absolute value of x minus y to be less than delta 2. But maybe I'll need something else too. In fact, maybe there's a spoiler that I definitely did because there are two spaces there.
We want delta 1 and delta 2.
That seems reasonable. Let's put it there and see if it gives us everything we need. I guess delta 1 and delta 2 would be a more intuitive order to put them in. So if you were going back and doing your rewrites, delta 1, delta 2 would probably be the right choice. Right order to put these in. And I'll continue to put the delta 1 in green because I might need to divide delta 1 by 2. Nice. So I would like to know that the absolute value of, let's see the argument from here. So I have this point P that I started with. I have this point X, which is also a limit point. I know that that distance is less than delta 1. I've cooked up this thawed point Y, which is actually in U. And I know this length is less than delta 1 and is also less than delta 2. So there's a picture of some things I know. Let's draw the corresponding thing for the output values. There's G of P. My whole goal is G of P is close to G of X. So there's the edge of this triangle I would like to be small. And there's G of Y, which happens to be the same thing as F of Y, since Y is in U. And let's see what we know right now. Do I know that F of Y is close to G of X? Yeah, because this length is less than delta 2. That's nice. So that's, if you like, summarized right here. Since the absolute value of x, 0 is less than the absolute value of x minus y, is less than delta 2, then by the very choice of delta 2, we see the absolute value of g of x minus g of y is less than epsilon 0 red. So if I could get f of y to also be close to g of p, that would make me happy, right? That would do the job. But I would have that. I would, as long as y were close to p. But I guess, according to this picture, is y close to p? Yeah. If y is close to x and x is close to p, then y is close to p. But let's see what bigness we have here. So I guess this distance is less than delta 1, that distance is less than delta 1, so this distance is less than delta 1 plus delta 1. Well, that's kind of annoying, isn't it? My choice of delta 1 doesn't tell me anything if the distance between y and p is less than delta 1 plus delta 1. The distance between y and p needs to be less than delta 1. So what's the solution? Divide by 2. So instead, only in the proof, I'll assume that the absolute value of x minus p is less than delta 1. So let's see. Then I'll get the absolute value of x minus p is less than delta 1 over 2. Notice that's still less than delta 1, so we still have that hypothesis. And so we can still conclude that the absolute value of g of p minus f of x is less than epsilon. But let's head down here. This is where something interesting is going to happen. I guess this had better be divided by 2 also. So I know that absolute value of x minus y is less than the minimum of 2 numbers. So in particular, it's less than either of those 2 numbers. So it's less than delta 1 over 2. Now, way early on, we already knew that the absolute value of x minus p is less than delta 1 over 2. And so we wind up with the conclusion that, well, that's wrong. The distance from p to y, and I mean the order doesn't matter, is less than delta 1 over 2 plus delta 1 over 2. And if we happen to know that y was not equal to p, then we would have 0 is less than the absolute value of y minus p is less than delta 1, because delta 1 is the same as delta 1 over 2 plus delta 1 over 2. since the distance from y to p is less than delta 1, we can conclude that the distance from f of y to g of y is less than epsilon. So what conclusion can I make about the distance from g of p to g of x by the triangle inequality? Less than 2 epsilon? Which again isn't what I want, but I know how to fix it, right? What do I need to do to fix it? Divide by 2. So I'm still happy for the first half of the proof because epsilon over 2 is smaller than epsilon. Down here, let's divide that epsilon by 2 as well. But I could put any positive number I wanted there. Epsilon over 2 is positive, so that's still fine. So then let's see, how does this run? Since the absolute value of 0 is since 0 is less than absolute value of x minus y is less than delta 2, I conclude that g of x minus f of y in absolute value is less than epsilon over 2. Great. Additionally, I have right now absolute value of y minus p. At 0 is less than absolute value of y minus p is less than delta 1. So that means, by this if then, I have 0 is less than the absolute value of y minus p. So I can conclude that the absolute value of g of p minus f of y is less than epsilon over 2. Let's see, I also have right now absolute value of, well, I mean, I said this earlier. Yeah, g of x minus f of y. Yeah, both of these are less than epsilon over 2. So I can use the triangle inequality to now conclude that the absolute value of g of x minus g of p is less than epsilon over 2 plus epsilon over 2, which is also known as epsilon. Which is the conclusion I needed, right? So I got a little bit confused, I think, close to the end, but people are pretty happy with the proof. So let's move on to the actual topic for today. So there's one last rule that I have in this class, and that's power series. So let me kind of just remind you informally of what a power series is. So how many people, like, maybe here's the one Taylor series you should just remember. The Taylor series for e to the x is the sum from k equals 0 to infinity of 1 over k factorial times x to the power k. And either you remember it or you don't. That's the Taylor series for e to the x. How many people remember that from Calc 2? Okay, that's somehow about the number that I expect. Maybe even a little bit more than I expected. But what does that mean? So on this one hand, this should mean like something about a limit, right? So this should mean that e to the x is like the same as the limit as n goes to infinity of this sequence of partial sums. Okay, cool. So there's one definition. And I guess that just means like for every x, e to the x should be this limit. And that would give us one idea of what it means for a sequence of functions to converge. But what do you think? Should e to the x be continuous? So we better develop some theory so we can prove that power series are continuous. And that's what we're going to start doing. And the first thing that we'll see is that this definition of convergence, just for each x value you have a convergent sequence, is not enough to guarantee anything. You can get garbage out of that. So let's start talking about convergence of sequences of functions. This is a fat pattern. packet because it contains at least 2 topics. So that's our goal. We want to study things like power series, which we want to understand as limits of partial sums, but each of these partial sums is like a function. So we want to study limits of sequences of functions. Let's even start with this. What is a sequence of functions? So a sequence of functions should be like some, rule that takes a different each natural number of n and returns a function. So, I mean, there's one way to write that down. Let's let u be a subset of R. For each n in the natural numbers, let's let f sub n be a function on u. Then f sub n is a sequence of functions. Because, right, of course it is. On the other hand, maybe there's a different definition you could write. A sequence of functions is a function big F from the natural numbers cross some subset of the real line to R, which is defined via the rule f of n comma x is f sub n of x. There's another way to understand what a sequence of functions should be. So there's all the sequence of functions. It's just for each different natural number you have a function. Just like that. And just like that, you can start asking about limits. And here's one notion of a limit. Another function f from u to r is called the pointwise limit of the sequence of functions fn if for each x value, the sequence of real numbers given by f sub n of x. Right, that's now a sequence of real numbers. Each different natural number will give me a different value for f sub n of x. Possibly different value for f sub n of x. If that sequence of real numbers converges to f of x, which is a real number, then I'll say that the sequence of functions f sub n converges to f on the domain U. That seems like a reasonable definition, right? That's, I guess, like the most obvious definition. It'll also turn out to be not good enough in terms of actually having good properties. In order to see how to fix it, let's quantify everything. So let's quantify this. So up here it says, for each x in u, the sequence of real numbers f sub n of x converges to f of x. Well, we know what it means for f sub n of x to converge to f of x. Let's just expand it. For each x in u, I get f sub n of x converges to f of x. Well, what's the epsilon n definition of that?
There exists a big N such that for all little n bigger than big N, the absolute value of f sub n of x minus f of x is less than epsilon.
What's missing?
We need to have an epsilon.
But that's just the definition of convergence for a sequence of numbers. So we say that a sequence of functions converges pointwise on a domain U if for every x in U and for every epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, the absolute value of f sub n of x minus f of x is less than epsilon. So let's take a look. If you were to try to prove something is a sequence of functions converges pointwise, how would you do that? You would say, well, let's consider any x in u. Let's consider any epsilon bigger than 0. I now need to come up with a choice of big N. What things can your big N depend on?
Epsilon and x.
Epsilon and x. So that means this is a notion of convergence where different x's might require different choices of big N. So I'd like to uniformize this. So all choices of x have the same choice of big N. I don't want big N to depend on x anymore. Just like uniform continuity, how would you want to change this definition so that big N doesn't depend on x?
Define x later.
Just put the for all x after the there exists an N. So if you wanted to uniformize this definition, you would say, well, it should be something like for all epsilon bigger than 0, there exists a big N such that for all x in U and for all n bigger than big N, absolute value of f sub n of x minus f of x is less than epsilon. So there's now a new definition of a different thing, something stronger than just pointwise convergence, which I will call uniform convergence. Let's let f sub n from U to R be a sequence of functions. For some other function f from U to R, I say that f is the uniform limit of the sequence of functions f sub n if, for every epsilon bigger than 0, there exists a big N such that for all little n and big N, if little n is bigger than big N, and for all x in U, absolute value of f sub n of x minus f of x is less than epsilon, which might not be verbatim the same as was written on the same page, but do you see how it's like logically equivalent to? And so I mean, maybe the observation now is, well, we'll read that big N can depend on anything that's declared before big N, because those are the things that it knows about. So what can big N depend upon?
Epsilon.
Epsilon. And I guess like it might depend on the sequence of functions, but of course it does. So now I've given you two different definitions of convergence of sequences of functions, a pointwise version and a uniform version. Many people think I might ask them a pop quiz at the beginning of class next time. As long as I remember to do so. Which, you know, is maybe like 60-40, I remember. There's a good reason to do this. Pointwise convergence tends not to preserve good properties of functions. Uniform convergence, on the other hand, does. In order to see this, let's consider a particular sequence of functions. And I picked this example because it's going to demonstrate some properties that I want. So let's consider the functions, it's right there. Let's define f sub n on the interval from 0 to 1 to the real numbers. Let's define it by the rule f sub n of x is equal to x to the n. Let's define f of x to be 0 for all x's between 0 and 1, excluding 1, and define it to be 1 if x is equal to 1. Then I claim this sequence of functions converges to f pointwise on the closed interval from 0 to 1. That for any c in the interval from 0 to 1, excluding 1, so any number that's strictly less than 1, f sub n converges uniformly to f on the closed interval from 0 to c. But this sequence of functions, f sub n, does not converge uniformly to f on the closed interval from 0 to 1. And let's maybe even just look at some pictures, see if we believe that these things actually converge. So there's f sub 1, f sub 2, f sub 3, f sub 4. There's x sub n when n is 10 through 40. X sub n where n is 70, 80, or 90. And there's this limiting function, right? It's 0 until x is 1. When x is 1, the function is 1. Does it look like these y values are getting close to those y values? I think so. So yeah, I think I believe that these things converge pointwise. Uniform convergence is maybe harder to talk about. So we'll see that this convergence is not uniform. Now tell me, is that last function, is it even continuous? No. Where is it discontinuous? With this x value, it looks like there's a discontinuity.
Oh, yeah.
So at x equal to 1, it's not continuous. So here's a sequence of continuous functions, nice functions, which converge pointwise to a discontinuous function, a bad function. So pointwise convergence has screwed up this function. See how I didn't swear at you this time? But I mean, let's start somewhere. Let's prove that this convergence actually happens. So let's define f sub n to be the function that f sub n is defined to be in the theorem. Let's let f of x be the thing that f of x is defined to be in the theorem, proposition. So let's prove claim 1 first. Let's prove pointwise convergence. So what do? We consider any x in the domain. Zero comma 1. Let's consider any epsilon bigger than 0. Now I need to come up with some choices of big N. It looks like at the very least f of x is really different when x is 1 as opposed to when x is anything other than 1. So our choice of big N can depend on x. So when x is 1, let's let n be something that we get to pick. When x is not 1, let's let n be something that we get to pick. Let's assume that little n is bigger than big N. I need to show that absolute value of f sub n of x minus f of x is less than epsilon. And let's go through this argument why, and as we go through it, we'll figure out what big N needs to be. So let's see. When x is equal to 1, then f sub n of x minus f of x is equal to, well, let's see. What's f sub n of x when x is equal to 1? I guess it's like 1, right? Because 1 to the n is 1. What is f of x by definition when x is equal to 1? 1. And what is that equal to?
0.
And that's less than epsilon because epsilon is by assumption bigger than 0. Do I actually care what big N is when x is equal to 1? But you got to put something there. It doesn't matter what I put there, right? I never used it, but you need to say what big N is equal to. On the other hand, if 0 is less than or equal to x is less than or equal to 1, then, well, let's play the game. What's the definition of f sub n of x? X to the n. And what's f of x? 0. And I guess that simplifies to just x to the n. You don't even need the absolute values, right? Let's see, this x is a number that's less than 1, and this little n is bigger than big N. So how does x to the little n compare with x to the big N? Maybe a good way to get a sanity check is, what's like a sample number that's less than 1 but bigger than 0?
1.5.
Good. And let's see, I know that little n is bigger than big N, so let's let that be like 50. Which one of those is big R?
5.
Okay, cool. So it looks like x to the big N is the bigger one. This thing might be 0 though, in which case they'd just be equal. So this is less than or equal to x to the big N nice. So do you think you could take x to the big N, set it equal to epsilon, and solve for big N? Yeah, show that. Let's go to the side and do that. So let's see, x to the big N equals epsilon. If you were to try to solve that for big N, what would you wind up writing? Well, you would use like logs to do it, I guess. log base x of a number when x is equal to 0. Something like that. So there's a problem when x is equal to 0, but you know what, I think when x is equal to 0, f sub n of x is 0, but so is f of x, so the same argument as when n equals 1 walks. So there's an oversight here. X equals 0 needs its own case, but whatever. It's a super easy case, right? What choice of big N do you think should walk when x is equal to 0? What's f sub n of 0? That should be like 0 to the n. What's 0 to the n? 0. What's f of 0? So you're done. So x equals 0 needs its own case, but it's a really easy case. Nice. So what do people think? Do they believe that this sequence of functions converges pointwise? Wow. Let's try to prove the next claim. Let's try to prove the uniform convergence claim. Namely, that the sequence of functions converges uniformly on the interval from 0 to c, where c is any fixed number between 0 and 1, strictly between 0 and 1. Let's try to do it. Let's fix some of c in 0 and 1, so that 0 is less than or equal to c is less than 1. Let's consider any epsilon bigger than 0, because we're trying to prove something about uniform convergence. Big N is now going to be something that I get to choose. And now I'll consider any x in the domain, that is from 0 to c, and any little n bigger than big N. And I need to show that the absolute value of f sub n of x minus f of x is less than epsilon. And let's do that. Absolute value of f sub n of x minus f of x, what does that simplify to? That's like the same as the last page, right? Right, since x is less than or equal to c and c is less than 1, x is definitely less than 1, so I don't need to worry about the case that x equals 1. And let's see, x to the little n, x is less than c. So let's see. If x is less than c, then what can you tell me about, can you tell me something, if x is less than c, can you tell me something that's strictly bigger than, well, that's less than, if x is less than or equal to c, can you tell me something that's bigger than or equal to x to the n? C to the n. And I know that each of these are between 0 and 1. So how should c to the little n compare with c to the big N?
Should be less than.
Or maybe equal to. So, using all that, no, that's less than or equal to. Do you think you could now take that? You know what? Let's not allow c equals 0. C equals 0 is a silly case anyway. The interval from 0 to 0 isn't even an interval. Could you take c to the n and set that equal to epsilon and solve for big N? What would you get?
N is log base c of epsilon.
Yeah, n is log base c of epsilon. So you just told me a choice of big N, log base c of epsilon. Let's just take a gander at that. Does that depend on x? Nope. It depends on c, but c was a parameter defined before it in the statement. So that's okay. And it depends on epsilon, but of course it depends on epsilon and should have to depend on epsilon. Cool. So we get the uniform convergence. People feel pretty good about that? Finally, let's prove the non-uniform convergence claim. And so let's just even see what we have to prove. So let's write down the statement of uniform convergence to see what happens when we negate it. So we need to, uniform convergence means that for every epsilon there exists some big N such that for all little n bigger than big N, and for all x in 0, 1, absolute value of x sub n, f sub n of x minus f of x is less than epsilon. What we want to prove is the negation of that. We want to prove that the sequence of functions does not converge uniformly. Let's negate that. So instead of before all epsilon, we need.
Sorry. You want me to state it?
Yes.
Okay, so there exists an epsilon greater than 0 for all delta greater than 0, such that there exists an x and a in the set, and scratch that and. Absolute value of x minus by a is less than epsilon, and the absolute value of f of x minus by f of a is greater than or equal to epsilon.
You accidentally negated continuity instead of convergence.
Sorry about that.
No, you're okay. So you'll get there exists an epsilon such that instead of there exists an n, there will be a for all n. Instead of a for all little n, there will be an exists a little n bigger than big N, and there exists an x in 0, 1. Does it matter what order these two things come in? No, they're universally quantified either way. So that order doesn't matter. And these things need to satisfy the negation of this. So that's what we need to show. We need to show that there exists an epsilon bigger than 0 such that for all big N, there exists a little n bigger than big N and an x in the interval from 0 to 1 such that the absolute value of the difference f sub n of x minus f of x is bigger than or equal to epsilon. And in order to come up with, because the first line of this proof is going to be let epsilon be a number. And it can't depend on anything, it'll just be a constant. In order to come up with what constant we think should work, let's check out these pictures. So there is the graph of f sub 100, f sub 200, and f sub 300. Although in reality the graphing tool used by TIX is not so reliable for computation, so I wouldn't trust these graphs completely, but they look, I mean, you know what the graph of x to the 100 should look like, something like that. Notice this is just from x equal to 0.95 to x equal to 1. So if you look at, say, that x value, is that y value very close to the y value you'll get for f of x? Well, remember f of x has graph equal to that. So if I take that x value, does it look like the corresponding y values are very close? And in fact, by picking my x values carefully, how far apart could I get these y values to be?
Almost 1.
Almost 1. But if you said 1, I would have said, well, not quite. But if you said anything less than 1, I said, well, you could do better than that. But we don't need to get like the best choice. So we can exceed apparently any quantity less than 1. What's a quantity that's less than 1? pick like a number though. We aren't trying to depend on anything. What's a constant number that's less than 1? 1 half will do. So we'll let the it off. 3/4 or 7/6. But there's a choice of epsilon that should do the job. Let's let epsilon be a half. And these pictures told us that epsilon equal to a half should walk. But these pictures also tell us epsilon equal to 1 will definitely not walk. So then we need to show something for every big N. So let's consider any little n bigger than big N. It looks, in fact, like it doesn't matter what little n is. So what's a choice of little n that's bigger than big N?
2n, n plus 1.
I'll say big N plus 1, because someone might be an ass and like, yeah, 2 big N should walk. Because let's consider any big N in the natural numbers. 2 times n will walk 2. And then let's figure out what x value we should use. And I guess we'll figure out what x value we should use by like doing the walk. Cool. So I guess the x value that we use had better not be x equal to 1. Is that x equal to 1, f sub n of x and f of x are equal, so they're not far apart. So when that's the case, absolute value of f sub n of x minus f of x is equal to x to the n. And we want to come up with a choice of x, which is bigger than or equal to epsilon, which is 1/2. So do you think you could take x to the n equal to 1/2 and solve that for x? What would you get? Sorry, I zoomed out incorrectly. There. If x to the n is equal to 1/2, what's a choice of x that solves that equation? How about the nth root of 1/2? Let's let x be 1/2 to the 1 over n power, or if you're the type who prefers roots, the nth root of 1/2. For that choice of x, if x is the nth root of 1/2, then what's 1/2 to the 1 over n raised to the nth power? Which is bigger than or equal to 1/2. Bigger than or equal to epsilon, because epsilon is equal to 1/2. In fact, it's equal to epsilon. So what have we done? We considered any epsilon bigger than, we came up with an epsilon bigger than 0, namely 1/2. We considered any big n, so for any little n, there exists a little n bigger than big N, and a choice of x, namely the nth root of 1/2, such that absolute value of f sub n of x minus f of x is bigger than or equal to epsilon. So this thing is, the sequence function fails to converge uniformly. Cool. So, well, I'm out of time. In fact, I'm about a minute 20 over time. So here's what I'll suggest you do in advance of next time. This set of notes is supposed to take a few days. So I don't feel too bad about schedule yet. There are 4 questions on this page and the next. I would like you to meditate on those yes-no questions in light of the example we just came up with, and try to decide if you have any intuition about whether the answers are yes or no. And that's where we'll start. We'll start with an informal poll. No, we'll start with a pop quiz, then an informal poll.